So I built another AI supercomputer, and this one's crazy. 1, 2, 3, 4 Mac Studios, 512 gigs of RAM each, 2 terabytes of unified memory. This might be the most powerful local AI setup ever built. But hold up, I've done this before. Earlier this year, I clustered together 5 Mac Studios, and it was kind of terrible. I expected it to run AI models like a champ, but actually adding more computers made it slower, 91% slower. Everyone said clustering was stupid, and they were right. So why am I doing this again? Well, Apple just dropped something new, a simple software update that might change the entire game, something I was begging for. So in this video, we're clustering again. We're gonna throw the biggest, baddest AI models at this cluster and see what it can do. Our goal is to answer this one question: does clustering local AI actually make sense for us? Will it actually be fast, or will it just suck like last time? Get your copy ready, let's find out. Now, Apple was watching me. In my last video, I said this: I don't know how XO Labs is gonna solve that though, because we're at the mercy of what hardware we have. And this, I would love to know what the experience would be with some like serious connectivity between the GPUs of these 5 Mac Studios. I was honestly pretty bummed about the performance of that cluster. I had such high hopes. I know you probably did too. But Apple listened and they did something about it. And they also sent me something. This. This setup is insane. I wasn't sure if they were gonna send me this, but I was shocked when they said yes. They sent me their biggest, baddest machines fully spec'd out. But hold up, my old cluster had 5 Mac Studios. How is this better? Watch this. Now these machines are ridiculous. Each one of these Mac Studios has 512 gigabytes of RAM. RAM. That's a hard drive for some computers. And this is unified memory, meaning the GPU can use it. So let me put it this way: 512 gigabytes of GPU memory, of VRAM. They have 8 terabytes of storage, 80 GPU cores, and if we do the math, this monster cluster has 2 terabytes of unified memory, 32 terabytes of storage, and 320 GPU cores. This is Maxzilla. Compared to our old cluster running M2 Max, it's not even a comparison. It's kind of silly, because even though we have 1 less Mac, each of our machines has 8 times the memory. So we have 6.4 times more RAM. We're doubling our GPU bandwidth, and this will make a huge impact. We're doing Thunderbolt 5 versus Thunderbolt 4, which is also double the bandwidth. The only thing that makes you kind of go, oh, that hurts, is the price of this cluster, $50,000. I know. But seriously, think about it. What's the alternative to do something like this locally? Like if you wanted the same specs from an NVIDIA H100 cluster, you would need 26 H100s, each with 80 gigabytes of VRAM. That would cost you over $780,000. And it's actually more than that if you build out the system. We'll talk more about that later. But the point is, this cluster is ridiculous. Okay, cool. We have these big, amazing monsters, but the biggest issue we had last time was networking, the bandwidth. What did Apple do? We'll get to that. But first we have to actually connect them, right? That's the whole clustering part. Now to make this work, I had to connect them via Thunderbolt and Ethernet. Thankfully, I had a spare UniFi switch that had some 2.5 gig ports, which I desperately needed because downloading these models, they're huge. The largest one I had to download was 735 gigabytes, and I had to download that on each of the Macs. I also had to make sure my uplink was 10 gigabit Ethernet because goodness, this took forever. We're also using the Ethernet so the cluster can see each other, but it's not how they're actually connecting and exchanging information. That's where Thunderbolt comes in. I was given this very fancy diagram to connect them just so in a mesh. It's just a little meshy. Sorry, I had to do it. Now let's take a step back and look at this for a moment. Isn't this beautiful? I honestly think this might be the most powerful local AI setup ever built. Prove me wrong. What can beat 320 GPU cores, 2 terabytes of unified memory? This cluster should be able to handle anything. And notice our asterisk here, should. Because it really doesn't matter how powerful these Macs are if the connection between them isn't super fast. And that's what killed it last time, the networking. Running bigger models didn't matter because everything came down to a crawl. And even though we're doubling our bandwidth with Thunderbolt 5, we still have a massive networking problem: latency. But Apple changed the game completely with the software update. That's it. Check this out. You know what really bugs me? When the problem is actually networking. Everybody blames networking, but this time it was actually true. When I ran these models on 5 Mac Studios, it was 91% slower. It wasn't the GPU, it wasn't the memory, it was the networking, it was that latency between the connections. I mean, look at these speeds from last time when I clustered them together. It's bad. But Apple said they solved it. Let's see. Actually, let me just show you real quick. Let's see if they did it. Don't stare at this too long. This is your sneak peek. Here's the old way. Ooh, 5 tokens per second, not great. Let's try Apple's fix. Now that's a lot better, 15 tokens per second. That's 3 times faster. Same model, same cluster, but what are they doing? How do they make it faster? It's networking. It's always about networking. Now, the way they solved it is actually pretty simple. They just increased the speed of our Thunderbolt connections. And I'm not talking about going from Thunderbolt 4 to Thunderbolt 5 and doubling that bandwidth. No. The metric we're looking at is latency. How quickly a packet or a message can go from MAC to MAC. Now, currently this latency is around 300 microseconds, which I know sounds pretty fast, but not in the AI world. And because of this latency, we were stuck with something called pipeline parallelism. That's a fun word. 10 times fast. Pipeline parallelism. Pipeline parallelism. How far did you get? It's essentially a technique we use to split up a model between multiple systems and a cluster. For example, let's take an AI model like the Llama 3.37dB, FP16. That's some good precision. A model like this will have around 80 layers, which essentially is a series of filters that your prompt will pass through to help it respond to you. So if you say, hey, what's the capital of Japan? It might process it like this. Each layer is doing some fancy math on the input and passes the result to the next layer, each layer refining the answer until you get your response. Now, when you cluster this model, it divides up the layers between each machine. So Mac 1 would get layers 1 through 20, Mac 2, 21 through 40, and so on. But here's where it gets painful. It's sequential. So for every token, Mac 1 processes layers 1 through 20, stops, sends the results to Mac 2. It'll process layers 21 through 40, stops, and then so on. It's like a relay race with really fast sprinters, but we're not working together. We're waiting on each other. Now, pipeline parallelism is awesome because it gave us capacity. We could run large models that we can never run on one machine and run them on multiple. But what it didn't give us was speed. Instead, we got a waiting room. But there is a better way, a faster way, and it's called tensor parallelism. I know we're getting a little nerdy. Coffee break real quick. This is the much smarter way. Instead of each Mac owning layers and processing them sequentially, all Macs work together on every single layer. Here, we're not dividing the layer. We're dividing the math. So for layer 1, Mac 1 does 25% of the math. Mac 2 does 25, 3 25, 4 25. When they're done, they combine the results. Now in theory, this is supposed to be 3.5 times faster than pipeline parallelism. Goodness, that phrase kills me. So cool, let's just do that. That's the solution. We can't. Our networking still sucks. And it's even worse with this method. Because for each Mac to work on one layer at a time, lots of communication is happening. It's like a group project. Lots of messages being sent back and forth. In fact, we're talking 2 convos per layer. So for every token, we have 160 convos happening. Let's do some math here. Assuming each message takes about 300 microseconds. Now I know microseconds is this little symbol here. I just can't draw it. I can't do it, I'm sorry. Times 160, that's nearly 50 milliseconds of waiting per token. So because of our networking latency, tensor parallelism actually ends up being slower than pipeline parallelism, which is why we couldn't do it. All that chit chat killed it. If only our network was faster, if only latency was solved. Well, that's what Apple did. They made it faster. And I'm not kidding, it was just a simple software update. Apple quietly enabled in Tahoe 26.2 a technology on their Thunderbolt ports called RDMA, or Remote Direct Memory Access. This is huge. We're in the big leagues now. We're not playing around. Now, you may have heard me mention RDMA before in a previous video talking about AI data center networking. You can watch it right here. It's what AI clusters and data centers use to talk back and forth at extremely high speeds. It's what models like ChatGPT and Claude use. But what is it? Well, let's talk about what life is like before RDMA with our Thunderbolt 5 connections. These connections right here are essentially just network connections using good old TCP/IP, the traditional networking stack. Now that's a problem for us here because that introduces overhead, increasing latency. Because every message is having to go through a few steps, doing things like being processed by the CPU before it can even hit the GPU memory. And I have no idea where the CPU and the GPU is in this Mac Studio. I'm just making stuff up. It's this traditional networking processing that's causing our latency. But with RDMA, we skip all that. RDMA is direct memory access. We remove the TCP/IP stack, say, nah, we don't need you anymore. We're getting a direct connection. No more stops. A direct connection from GPU memory to GPU memory, GPU to GPU. That's the direct memory access part. And here's what this does. This takes our latency from 300 microseconds down to 3 microseconds. Are you kidding me? That's a 100x increase, or decrease. That's a bullet train. Direct connection. So now with our cluster, we no longer have to worry about IP addresses, TCP/IP overhead, all that CPU processing. No. We have a direct connection between the GPUs with these Thunderbolt 5 ports. Direct memory access. This solves our latency problem. And again, it was just a software update. What took them so long? Seriously, Apple. I'm sorry. I'm grateful for just it being here. I'm sorry. Now, in theory, this sounds awesome, but does it actually work? Now, you saw a teaser already, but that was just a smaller model. What happens when we actually throw some crazy large models at it, like the largest models available right now? Will it work? Will it make clustering actually useful? Let's find out. with the software that you all thought went away, but it's come back with a vengeance. Hey, I'm outside right now. Why? Because I want to tell you about our sponsor today, TwinGate. Because check this out, I can't access my lab right now on my laptop. I'm trying to connect to our cluster and it's not working. It's because I'm not using TwinGate. Watch this. I'll simply click connect, authenticate because it's really secure. And by the way, this is not VPN. No. This is better than VPN. It's more than VPN. Okay, cool, we're authenticated. Now let's try it again. It better work. You know what? It's still not working. I don't have access. But you're probably thinking, Chuck, wow, great ad. You tried to show us you didn't have access and tried to give yourself access with TwinGate. It didn't work. That's by design. TwinGate is zero trust network access. You can set it up. You can install it. It takes you about 5 minutes. You can use a Raspberry Pi, whatever. It's free for up to 5 users with your home network. It's a no-brainer. Just do it. But also, you have to specifically, explicitly allow access. So let's do that right now. I'll create the resource, and then here's where I give access. I'm only giving access to admins. Now let's try it again. Fingers crossed. We're in! And I'm checking on my cluster to see, I'm downloading a new model right now, Quincoder. Oh, you're not supposed to see this yet. You got a sneak peek during the ad. Look at you. But seriously, if you're not using TwinGate, what are you even doing? VPN is old. And if you're like, Chuck, I don't need TwinGate, yes you do. You have a home lab, right? That's where you're watching my channel. You do local AI, you have Plex. How are you accessing that when you're out in the field? Seriously, just get signed up. It's free. Check the link below, twingate.com/networkchuck. And seriously, thank you to TwinGate for making this video possible. I couldn't do this kind of stuff without them, so check it out. All right, now back to the video. And it's getting cold out here. I gotta go back inside. Now, a lot of people thought Exo Labs threw in the towel. Even Jeff.
Exo stopped development like 5 months ago, and even simple fixes are being ignored.
So did they give up the dream of clustering AI with consumer hardware? Nope. They're here, they're alive, and they're working with Apple to resurrect clustering. A flashback earlier this year. I used Exo Labs to cluster my 5 Mac studios together. It was still pretty new, rough around the edges. And it's kind of an amazing software, an amazing idea, because you can cluster any hardware together. But the networking, that was a thing. So when Exo Labs and Apple both reached out to me, I said, hey, we got a new update. We got a thing we've been working on and we think it's gonna solve your clustering networking issues. And they said, do you want in? And I'm like, dude, put up that bat signal, I'm there. So fast forward, here we are. I have the Macs. I got them connected according to our official diagram. I installed the beta Tahoe 26.2 update. And here's the real magic. I had to go into recovery mode and enable RDMA. Seeing that RDMA enabled, that got me excited. From there, it's pretty much smooth sailing. I installed the super secret beta version that Exo Labs gave me, which I think might be available right now. I could be wrong. I'll have more info below. But look at this, it got a facelift, right? Before this was a CLI only tool, which I'm fine with, but now we have a native Mac app and it's gorgeous. So here we are, after a few software patches from Exo, my cluster's connected. And as you may have seen earlier in our sneak peek, we have the option of running in dumb mode, pipeline parallelism, or tensor parallelism. Just for fun, let's do it the old way once more. So we'll select our pipeline and MLX ring, we'll select 4 nodes using our entire cluster, and we'll choose our Llama 3.370B FP16. Load that sucker up. Now it's actually pretty fast loading up. This is so fun. It's ready, and keep in mind, this is the dumb old slow way. 5 tokens a second, around 200 milliseconds per token. Goodness, that's really slow. I could already have my cup of coffee by the time it's done. And let's try this. This is gonna be fun. Let's do tensor parallelism, but stay on the old networking, no RDMA. And let's see what it does. Keeping in mind with this, we're having 160 conversations every token. Let's load it up. It's ready. Let's see what happens. Oh, yeah, it's slower, right? I mean, we're talking half as fast, which wasn't a lot, right? We're at 3 tokens per second, 370 milliseconds per token. This ain't great. Oh, I mean, this is unusable. But let's add in Apple's magic. Let's enable RDMA. Tensor parallelism, RDMA, 4 nodes. Llama 3.370B, load that bad boy up. And this is actually really fast loading up. Look at those guys go. I love this new interface they have. It's ready. I mean, look at that. That's incredible. 16 tokens a second on average. 66 milliseconds per token. They did it. Apple, you're awesome. But this is a smaller model, right? There are bigger ones. What about DeepSeek? What about Kimi K2? How about both at the same time? Get your coffee ready, you're about to make this cluster sweat. I think. Let's go. Okay, so we just proved that tensor parallelism works with RDMA. It's fantastic, 3 times faster. But here's the real question. Do you even need to cluster? Like, does clustering make sense for you? Like, why not just buy one expensive Mac? Like, one of these guys has 512 gigs of RAM. What models do we need to run that could not run on that one machine? Let's test it out. Let's throw progressively bigger models on this thing. Let's throw all the models on it at the same time. Let's see what happens. Little coffee break. It's clustering time. I don't know why I said that. That didn't feel right. All right, here we have our cluster. Over here, we've got our metrics. Mach 1, 2, 3, and 4. Now I want to test all these models right here. But the first thing I want to test is kind of a tiny model. I want to see how the performance is on 1 Mach versus 4. I'm curious, with RDMA, will the performance be better? Because 1 Mach by itself, it can run that model fine. Let's test it out. So I'm just going to choose one node, and I'm going to load a small model, a little baby. Llama 3.2 3B, 8-bit. It's nothing. Launch. Okay, it's ready. And we're rocking 147 tokens a second. Let's ask something more involved. So that's fast. Let's cluster it. Okay, now with 4 nodes clustered, it's faster. Okay, so 240 tokens a second. That's awesome. That's 100 tokens faster than a single node. But look at it go. Maxing out that GPU across the board. Looks like it kind of lost the script somewhere in there. But it looks like we're pulling about, getting up to 100 watts per Mach. So 400 watts in total. Not bad. Let's keep moving up. Let's do a single node for the Llama 3.370B, FP16, because these guys can run it. So we loaded it up on Mach 2. We can see it's full right there. Let's see how it performs. Okay, 5 tokens a second. Not amazing. It's maxing out that GPU. Looks like 150 watts. I am changing the monitoring halfway through here because I think it's better. I'm gonna use MacTop. It's still going. But notice we still have plenty of memory on that second Mach, which is where it's loaded. All right, cool. Roughly 5 tokens a second. Let's cluster it. Let's load it up. Watch that memory fill up. It's so fun to watch it over here on the screen. This is a night and day difference compared to our last cluster. It took forever. You guys have no idea how painful that video was to make. Okay, it's ready. Okay, 16 tokens a second. Try a more intense prompt. And there it goes. Maxing out the GPUs across the board. Memory, 9% on each one. About 130 watts on each machine. This is a cluster, man. In a good way. Okay, let's move on. Let's up the game. I love watching the GPU memory go down as well. Okay, our next model. Let's do something a bit bigger. DeepSeek. Okay, I'm back. You didn't know I left. I had to troubleshoot some stuff. I don't have a Qwen model downloaded? I thought I had Qwen. I'm gonna have to let it download for a little bit. An hour? But I got it working. I had to download this new model I forgot to download. Anyways, here we go. We're gonna load it up. All right, so first we'll do one node, and we'll do the Qwen 3 Coder 480B. It's a big one, but again, our Macs have 512 gigabytes of RAM. Now this is a mixture of experts model, so it should be a bit faster because it's not using all parameters all at once. Let's launch it. And keep in mind, we're building our way up to the Kimi K2 thinking model, which is 1 trillion parameters. I can't even what? Yes, we can do that, I think. We'll see. All right, it's loading on one node, Mach 2. Mach 2 is blowing up. All right, he's ready. Explain MOE to me, Elif. 27 tokens a second, it's pretty good. Let's cluster it up. Powering down, pew. Tensor, RDMA, 4 nodes. Qwen 3 Coder, launching. Look at it go. All right, it's ready. And let's see what we got. 40 tokens a second. Okay, so it's nearly double the speed. So the story so far is clustering does not slow us down, it speeds us up, which is what we expected the first time around, right? Let's keep moving up. And keep an eye on the power and stuff. We'll have that on the screen. Let's do our next model. We'll do, actually, you know what? Enough messing around. Let's go Kimi K2. I don't think we'll be able to load this model on one node. Yeah, it's like at minimum, you gotta do 2, which is still crazy. We only need 2. Let's run it on 4 though. This is a massive model. 658 gigabytes per node I had to download. 1 trillion parameters. Let me just double check my math here. Yes, 1 trillion parameters. Oh my goodness. Okay, let's load it up. Let's watch this thing fill up. Here we go. Now this is like the best coding model right now for local AI. And even when people use cloud AI to code, they'll pay for this model on a hosted platform. It's that good. But here we're not having to use any cloud resources. We can host everything right here locally. It's still loading, filling up those GPU tanks. Okay, It's ready. It used 33% of the RAM on each one. Let's ask it a question. 1 trillion parameters. Let's see how it goes. Whoa. So it's thinking right now. Let's expand the thinking. But we've got 28, almost 30 tokens a second. Oh my gosh. And it's so cool it's thinking, right? Like, oh my gosh, a thinking model. I mean, this is fast. How much RAM is required to run the 4-bit model? Let's see, power. We're doing like 110 watts on each one. Now, one thing I wanted to show you guys, but I just could not show you, and that's the bandwidth, the latency, the network traffic. I wanted to see that, just how much stuff we're pushing. But right now, and you can see this now, oh, this thing's thinking. If I go to my network configuration, the Thunderbolt bridge is inactive, it's disabled. This is essentially ghost traffic, I can't see it. I can't monitor it. That might change, but I did ask Apple, I'm like, hey, please, give me a way to visualize this. And they're like, we can't do that right now. So, sorry. Pretend it's a lot. Because we have to assume that, right? 160 conversations every token. Let's have it create a Python script that can scrape websites. I mean, it's doing great. It's thinking. It's making my script now. This is local AI. Okay, but this isn't the whole story, right? So we've got some room. We're running the biggest model we could download right now, and we have some room. Let's go home, and keep in mind, we're gonna keep this model running. We're gonna load a new one. Just refresh my page so I get a fresh instance here. I'm gonna load this one. It's beefier, meaning like it's a 713 gigabytes. It is the biggest model they have. But it's only 671 billion parameters, like, which is so crazy. Our last cluster, we tried to run a 671B and it like destroyed everything. Now we're gonna run it alongside a trillion parameter model, which makes me feel accomplished, even though I didn't do anything. Let's launch it. Good job, Apple and Exo. So now let's watch this GPU fill up. So we're running Kimi K2 thinking, and what's this model again? DeepSeek 3.1 8-bit, 671B. Oh, it failed. I don't like that, but I know we can still do it. I'm gonna try again. I had to build these scripts with Claude Code that would reboot the cluster and reinitialize it because this happens with beta software, so hang tight. Okay, I'm back. Let's try it again. Had to reboot the whole cluster. Let's first try and load Kimi K2. I know we can do this. I know we can do this. Okay, we're loaded. Let's go DeepSeek. Come on, let's do this. DeepSeek. I believe in you. Launch. Come on, don't fail. Okay, we're loading. It's filling up. So far so good. I'm getting nervous. It's almost done, I think. We're at 50%, over 50% on each node. Those things are stressing. Look at the map down here. It's like, oh my gosh, 60%. Uh-oh, did we break it? Oh, it's still filling up. We did it. Okay, I'm even scared to talk to him though because I don't want to break it again. But we have to talk to it, right? So let's have a chat with DeepSeek. (27, 26 tokens per second). Let's switch to Kimi K2. And there we go. Like, we're using both models. We have both those suckers loaded up. That's crazy. How much more can we load? Let's do another one. Oh gosh. Let's load up Llama 3.370B FP16, because that's one of the other ones I have downloaded. And launch. It's loading. Okay. It's ready. Now the RAM utilization is kind of weird, right? Like, it went up to 60% and now it's back down to 50, but like, I know we have these models loaded. Let's go talk to Llama. Wow, what a dumb answer. I just want to verify I have everything loaded up. I'm going to switch back and forth. Oh wait, why did it? That was my, that's funny. That was my clipboard from earlier, because that's what I had to sneak and do to restart the cluster. Okay, and let's switch to Kimi. I'm not sure how to say it. I'm so proud of Apple and Exo. Y'all did so good. Now here's the thing, I can run other models, but I didn't download any other big ones, and that's the longest part. I'm not doing that again. But let's just see, what else do I have downloaded? I've got a few Llama variants. I mean, I'll pull up that 3.2 model from earlier. Let's just run that, if we have to do something. Actually, I do have Llama 3.370B 4-bit. Let's load you up, because we can. That's ready. Let's do another one. Let's grab the Llama 3.2 3B 4-bit. I think I have that one. Yeah, let's load him up. All right, that was easy. So we have 1, 2, 3, 4, 5 models running. But the memory usage is staying at like around 50. Actually keeps going down. I don't know why that is. So I think we answered the question. Clustering's awesome now. I'm running every model I can possibly run on it, and it's just doing it like a champ, and it's fast. But okay, so far we've just been stuck in Xo's interface. What about using real applications like coding or open code or open web UI? Like, can you use this with that? Let's find out. All right, let's try out open web UI because this is real. It's not just benchmarks. It's not just test software. Let's see what happens. I want to use my cluster here, or not my cluster, my OpenWebUI AI.Hogwarts.studio. I should already have my models loaded up here because Xo runs off of an API endpoint. Let's see. Let's find Kimmy. There it is. Let's do thinking. We'll see if it starts to stress out a little bit. All right, let's see what happens. Okay. Yeah, I mean, there it goes. It's freaking out over here. It's thinking. I mean, this is so cool. Look at this. I'm using OpenWebUI on a totally separate server in my server room, and it's connecting to my Mac cluster, running Kimi K2, a trillion parameter model. How awesome is this? It's thinking a lot. It's a very smart model. And tell you what, while it's doing that, let's go to this server here. I have Xcode installed, which is like Apple's VS Code. It's still going. Okay, it wrote it. So finish the app. I mean, that's impressive, what it did. That's so cool. All right, let's try Xcode. And I'm just gonna try looking at an existing project, Daniel Miessler's Fabric. Let's find some code here. Let's ask it to tell us what this code does. Let's talk to DeepSeek. This is so crazy. All right, it's going, it's freaking out. It's thinking over here. Look at that. And I'll try one more, let's try OpenCode. I love CLI tools to code and do whatever you want. Now I should already have the cluster set up. Yeah, there it is, actually K2 thinking sitting right there. Yeah, so it's freaking out over there. It's doing its thing. We can see the thinking, but I just wanted to show off that we can use any of these apps. Although I think it has a hard time using tools with OpenCode. All right, there we go. And then I'll switch models to Llama 3.3 and say analyze the code that was just created. Dude, it's going all out. It's making a whole freaking website. All right, I think it's done. I'm gonna try this. Oh, it's cute. It's cute. I'm gonna interrupt it and let Llama take over. Let's see while it's thinking here if I can still use OpenWebUI, because I think I'm stressing it out. Yeah, I'm trying DeepSeek over here. Yeah, it's fully stressed out right now. I think I locked it up. Okay, we did make it cry. Let's see if the web is still responsive. Now I'm gonna chalk this up to beta software. This is a bug that can be fixed, but now I need to tell it to die. So I'm gonna do that now. Restart my cluster. I don't want it to overheat in there. So are you impressed? Like, is clustering back? I kind of feel that way. Like, I was impressed with these results. Now sure, I'm running a $50,000 cluster, but it's a proof of concept. There's possibilities now. And we've come a long way since the beginning of this year where we just saw glacial speeds, but now it's functional. It's amazing. Now, full disclosure, Apple loaned this to me. I don't get to keep this. I wish. But I do have it for a little bit longer. What should I do with it? You have any ideas? I've got a $50,000 cluster. There's gotta be something else I can do. Let me know in the comments below. And of course, if you wanna see that last cluster video, if you haven't already seen it, it's right here. If you wanna learn more about RDMA and how AI networking works in the data center, I made a whole video about it here. No, I'm just gonna put it over here. I dive deeper into how RDMA helps us bypass all those roadblocks, those bumps in the road. Anyways, that's all I got. I'll catch you guys next time. Hey, real quick, this just in. Just a little extra info, a little mini segment on how Xo uses MLX, which MLX is how we're running all these models. It's Apple's open source machine learning framework that allows developers like Xo to do stuff like combining this stuff. Now here's what it says. RDMA over Thunderbolt driver enables MLX distributed to communicate.
Hey Chuck, I finished analyzing the call me back feature. Here's what I found.
Sorry, that was Claude calling me. So it says RDMA over Thunderbolt driver enables MLX distributed to communicate with low latency across Thunderbolt 5, enabling high levels of blah, 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 blah. Now what's cool is that MLX operations can run on either the CPU or the GPU. And this is without needing to move memory around because it's a unified memory. So seriously, shout out to the MLX team for being awesome. Xo worked closely with them on making this thing happen. And without them, this video wouldn't be possible. So I see you, MLX team. You're awesome. And you, watching this video right now, comment below and say thank you, Apple MLX team. Let's show them some love. Anyways, that's the end of your news segment. And yeah, I was reading my phone. There's nothing on this. Hey, you're still here. So at the end of my videos now, I like to pray for you, my audience. I know it might feel kind of weird. It is. I agree with you. But I genuinely care about you guys. And I want to see you succeed. I want to see you have lives of purpose and lives that are joyful. So anyways, I'm just going to pray for you. If you don't like that, it's fine. You can just click off. That's why I put it at the end. But let's go ahead and pray. Lord, I thank you for the person on the other side of the screen. I thank you that they're here, that they're passionate about technology, that they are excited for the future, and that even though AI may feel kind of overwhelming sometimes, they can see the light ahead. And I pray that they have, if they have any anxiety over AI or the job market or what the future is going to hold, that you would just ease those fears. And if they're worried about their current job that's going to go away, or if they're trying to find one, I ask that you just give them peace in that. That you would show them the path forward, because things are changing, let's be real. But God, you know what's going to happen. You know, you're not surprised by anything. So I ask that you just give us a path forward, give us wisdom, give this person wisdom, and I ask that you bless their family life right now. Everyone's got family, and I pray that you would, like right now I'm making this video on Christmas, so around Christmas time, so I pray that you would fill their hearts with joy, and you remind them of the importance of the people closest to them, and if they aren't close to these people, that they should do that now. Restore relationships, mend what's broken, fill them with peace. I saw a movie the other day, it's called That Christmas, and Christmas time is like a emotional magnifying glass, it said. If you're sad around this time, if you're lonely, it's going to magnify that, amplify it. If your heart's full of joy and you're surrounded by family, it's going to magnify and amplify that. So I pray for the people who are lonely right now around this time, that you would fill their hearts with joy. And that I'm hoping that during this season they can learn a bit of the reason why we take this time. Christmas, more Christ. I do believe that the ultimate joy can be found in you, Jesus, and I pray that this person on the other side of the screen, wherever they're at, they can just encounter you in some way, and whatever that means. Even in their doubt, even in their disbelief, it doesn't matter to you. Meet them there. I ask this in your name, Jesus. Amen. Sorry, that was a bit long one, but I feel like that was something I wanted to pray for you on. Anyways, that's all I got. I'll catch you guys next time.